6.1 Antiderivatives and Slope Fields. So chapter 6, we're going to start, learning indefinite integrals and slope fields, which is something new. And then in 6.2, we're going to talk about something called U substitution or integration with substitution. It's a technique that you use in finding out what antiderivatives are. Like instead of doing them in your head, it's kind of an algorithmic way of figuring out what the antiderivative is. And 6.3 is yet another technique in evaluating integrals. It's called integration by parts. So it's another technique in finding antiderivatives. But nothing specific to 6.1, like the technique. You'll just have to figure out, based on what you know so far about derivatives and antiderivatives, how to evaluate the integrals. There's also slope fields, which I'm going to talk about right away here. So if I have y equals 100 e to the 0.056 t, we'll say, and I wanted to find the derivative, so it would be dy dt. That would be, well, the 100 just floats, and then the derivative of e to the u is e to the u times the derivative of the exponent, which is 0.056. So I'll put that out front. So 0.056. So the derivative is this, and we know that y is equal to this, which is right there. So then you could just rewrite it as dy dt equals 0.056 y. Okay. Trying another one. So let's say y is 150 e to the 0.056 t. Then our derivative would be same thing. We'd have 150 floats. E to the u is the derivative, or is e to the u times the derivative of the exponent, which is 0.056. And if this is y, then that also is y. So we have dy dt equals 0.056 times y. So we notice that these two differential equations, it's a differential equation if it's a derivative equals this would not be differential because it's y equals, this is dy dt, so it's a differential equation. They're the same differential equation. So as long as it's in this form, we could do as many as we wanted to. We could do 50 e to the 0.056 t. Its differential equation dy dt would just equal 0.056 times what your y is. So it's the same thing. Dy dt equals 0.056 y. So if I was going to show you what dy dt equals 0.056 looks like on a graph, we make something called a slope field. Okay, this slope field gives a visualization of the solutions of dy dt equals 0.056 y. Okay, we can't show each individual, like there's an infinite amount. So slope fields generally on integer spots. So this might be 1, 1, this could be 1, 2, 1, 3, this would be 2, 2, 3, 3, and so on. Each individual dot on the graph gives you a line segment that represents the slope at that particular point. Notice that we have several original y equals, the exponential equation, the original equations here. They should fit into the slope field. This might be 150, this might be the 100, there's the 75, there's a 50 if I did all four of those. Okay, so the original equation should fit in the slopes of the slope field. So the individual little segments represents the slope field. These curves represent original solutions to the differential equation. All right, so here's another one. It's another slope field. So think of these kind of, I wrote a note, they're like weather maps. So if we wanted to talk about what direction is the wind coming from at this point, it's coming, from the northwest, you could say. And right here it'd be coming from the southwest because it's going up like that. So if I looked at just this point right there, -1, 3, this is our differential equation for this slope field. If I plugged in -1 for x and 3 for y, just plugged it into our differential equation, you're going to get 3. So I did the arithmetic here. You end up getting 3. Slope field at -1, 3, notice we would have a little line segment that has a slope of 3. So -1, 4 looks like it's a little steeper. -1, 5 might be 5. It's definitely steeper. -1, 1 is a flatter slope. So you might be asked on the AP exam to create a slope field. You might be asked to match a slope field with a differential equation. So just making a slope field, I'll show you what it looks like. Alright, so if this is, let's say dy dx equals, I'll say y over x. I don't know what that's going to look like. We'll see. Okay, so if x is 0, it's going to have, well, we won't talk about that. Let's try at 1, 1. So if I plug in 1 for x and 1 for y, we're going to get 1 over 1, which is 1. So at 1, 1, I'm going to make a slope that's 45 degrees, because that is a slope of 1. At 1, 2, 1 is x, 2. So 1, 2, I'm going to make it a little bit steeper, make a slope of 2. At 2, 1, maybe 2, that'd be 1, 1/2. 2, 1 would be 1/2. So it would be just flatter than that one. Might be like that. And 3, 1 would be 1/3. So it gets to the point where it's hard to tell between 1/2 and 1/3. How about -1, 1? So x is -1, y is 1, so we get -1. So 45 degrees, like that. So you can generate a slope field. How about 1, 0? 1, 0. So it'd be 0 over 1, which is 0. And you can't really tell, but it's on the x-axis. There it is. 2, 0 would be, as long as y is 0, we're going to get 0 on top. So 2, 0, 3, 0. These are all going to be horizontal. And 0, 0, we don't know what goes on right there. Okay, so that's how you can generate a slope field, just based off of picking all the points and then plug it into the differential equation, and you draw the little mini segments. I would say more times than not, slope fields are on the AP exam. I'm pretty sure they were on last year's exam. So I'll give you, in your assignment, I'll give you a few problems. There's a packet that has just a handful of slope field problems, because there aren't a lot of them in the book. Alright, so that's slope fields. We can do more of it because it might still be a little bit confusing, but also in this section 6.1, indefinite integrals. Now you've done indefinite integrals already. A definite integral is when you go from 1 to 4. Like this is a definite integral. Because there are boundaries of integration, you're actually finding the area under the curve from 1 to 4. So you find the antiderivative, plug in 4, minus, and then plug in 1, and you get your answer. So that's a definite integral. You do not need a plus c when you do a definite integral. Because, well, if this is x to the 1/2, the antiderivative would be x to the 3/2 times 2/3. So from 1 to 4. If we wanted to include a c, like plus c, to go from 1 to 4, now plug 4 in, I get, I'm just going to say 2/3, well, that's times 8, plus c minus 2/3 times 1 plus c. If you add the plus c every single time, the c minus c, those are going to disappear every single time. So you go ahead and put a c plus c in if you want to, but they're always going to disappear. So we don't even include them in antiderivatives when it's a definite integral. An indefinite integral is when you do a plus c. So if it's x squared dx, there's no boundaries of integration. Our answer would be 1/3 x cubed plus c. And then you can find c as long as you have an initial value. It's got to have at least one initial value in order to find c. If you don't have an initial value, you can't find c. So if I knew that y of 0 is 2, so then you can say y equals 1/3 x cubed plus c. You can plug 0 in for x, 2 in for y. So then c equals 2. So then you can find your original equation without the plus c because you have an initial value. Okay, so we've done those before. There's a good example in the book. This is example 8 on page 311. Well, I can show you, I guess. A heavy projectile is fired straight up from a platform 3 meters above the ground with an initial velocity of 160 meters per second. Assume the only force affecting the projectile during its flight is gravity, which produces a downward acceleration of 9.8 meters per second squared. If t equals 0 and the projectile is fired, find a formula for it. So we want to find velocity and the height. So we have, if this is ground, we've got our platform. And something is being fired. This is 3 meters high. It's going up at 160 meters per second. Okay, so we want to find the velocity and the height. Height could be s, which is position. Height is and position are basically the same thing. Okay, so we know that acceleration of gravity is negative 9.8. It's negative because it's going down. So then we can find the velocity, which is the antiderivative, plus c. And we can find that c if we know one initial value. Well, we know that when time is 0, our velocity is 160 meters per second. So you can plug 0 in for time, 160 in for velocity. So c is 160. So then my velocity equation, I'll say v of t, equals negative 9.8 t plus 160. So there's our velocity equation. So position or height, I'll say S is probably better. So S of t would be the antiderivative of that. That was 160t plus c. And again, we need to know one initial value, and we know when time is 0, our position is 3, because that's where what's being a heavy projectile was 3 meters off the ground. Okay, so our position is 3, our time is 0, so c equals 3. So depending on the type of an equation, you're always going to be your c. It is in these cases, but don't get in the habit of just saying c is 3 because that's our initial value. So S of t would be negative 4.9 t squared plus 160 t. Position at any given time of the heavy projectile. So we can say, when was the projectile 10 meters up? You could just make that 10 and solve the quadratic equation. When was the velocity of the object 20 meters per second? You could just set that in and you can solve for t. Or you could say, what's the velocity at 5 seconds? You can plug 5 in for t and you get the velocity at 5 seconds. I think that's all for 6.1.